Let's see. So a few years ago at Pi Caribbean, I had the privilege of seeing an earlier version of this talk. It would not be an understatement to say that it shaped pretty much every Python talk I've given since then. It's changed a lot about the way I think about programming in general, and I'm very excited to share it with you today at North Bay Python. Please welcome the author of Fluent Python, Luciano Ramalho.
Well, thank you very much, Christopher, Josh, the other organizers, everybody who's here. I actually forgot to change the title slide to put the North Bay Python logo. I will put it before publishing. But anyway, so this talk is about programming paradigms. And usually when we think of programming paradigms, we think of kind of categories where we try to put languages in those categories. But some languages overlap. Some languages don't really fit. But it's kind of a useful starting point, this idea of paradigms. But real soon you have to realize that these are very broad strokes. That's the problem with them. You have to be more detailed. So let's talk about concrete programming paradigms. This one is a calculator. I learned to program on the calculator on the left. And this is the manual of the calculator on the right. It shows the programming language, which was sort of like assembly, but you would also actually type the numbers. Anyway, so this book is interesting. It's kind of a panoramic view of programming languages, and they start with an example of the greatest common divisor algorithm in assembly, which looks very much like the calculator thing. And then in procedural language, C, OCaml, functional, Prolog, logical. And here's, for instance, two versions of GCD in Python. Now I would like to ask your participation. Who prefers in terms of this function, who likes the imperative style better? How many prefer the imperative style? And how many prefer the functional style? Okay. Yeah, that's really interesting. It's prettier. I guess it's more elegant. But it's not a very good fit for Python because of features that Python lack. Specifically a feature called proper tail calls, which allow recursive algorithms like that to be efficient. So now let's talk a little bit more about categories, because we like to categorize stuff. I think this is part of being human, and maybe even more part of being a programmer. But there's the Dewey classification system, right? I actually have a degree in library science. So this is the current edition, okay? This is not something from the 18th century. You have 10 top-level topics, and one of them is religion. You have a nice hierarchy inside one of those, but look at the categories for religion. So you have philosophy and theory of religion, the Bible, Christianity, Christian practice and observance, Christian orders. Everything is about, and then 290, there is other religions. Wow, that's great. And so starts with one that's no longer used, then there's classical religion, Germanic religion. I never heard of Germanic religion. Maybe it's what the Druids did, I don't know. And then there's religions of Indic origin, just one thing. Judaism. Oh, okay, so the Bible back there was not about Judaism, okay? It was... Anyway, so this is the end, okay? There's no more. The next topic is 300 social science. So there's this little corner for religions not provided for elsewhere, in which you can include, for instance, Buddhism. I don't know. But But the best classification of this kind that I know about is this one by Jorge Luis Borges, one of my favorite writers, an Argentinian writer. And he wrote a lot about books and a lot about books that don't exist. You know, he wrote fiction about books that are fictional. And one of the fictional books that he mentions is called, this is a Wikipedia article that describes it, is called The Celestial Emporium of Benevolent Knowledge, which was supposedly an ancient Chinese encyclopedia. And in it there was a classification of animals into 14 categories. So those that belong to the emperor, embalmed ones, those that are trained, suckling pigs, mermaids or sirens, fabulous ones, stray dogs, those that are included in this classification, those that tremble as if they were mad, innumerable ones, those drawn with a very fine camel hairbrush, etc. But that's not all. Those that have just broken the flower vase, and those that at a distance resemble flies. Okay, so that's, at least there's poetry. Okay, maybe the problem is that everybody who tried to do a categorization before was stupid, right? So let's talk about a classification that's rock solid. You know, the periodic table, everything is there because of a physical reason, a chemical reason, right? The structure of the atom, all right? Perfect. But has a misnamed column. Why is this called noble gases? First, the noble part is because they didn't, you know, get mixed up with the commoners, those gases. That's why they were noble, okay? Literally. And the gases part is also false because it was assumed that they would, those elements would always be in a gaseous state, but actually they can be liquefied. So there's lots of classifications of languages. I found this site called the I don't remember the language. I don't remember now. It's actually broken. These are just screenshots, okay? But that I took at the time. But they have like dozens of categories, okay, of programming languages. And then there's that book that I mentioned before. It's interesting because he doesn't commit to this concept of paradigms. But he has this sidebar in which he talks about, you know, you can classify, maybe, it's called example 1.3. Maybe you can classify languages. And then he offers this example of a classification, so declarative and an imperative. And then if you look closely, why is scripting? Why is that doing there? You know? And what's the technical reason for Smalltalk and Python not being on the same category, right? It's just, you know, academic prejudice. In my opinion, that's probably what it is, because, you know, Smalltalk has the academic chops. Anyway, so ontology is overrated, okay? That's the first part of the talk. Now, let's talk about the features, the idea of features. So there's the famous design patterns book, right? And it's interesting because in the introduction, which is really the best part of the book, they mention that our patterns assume Smalltalk-C++ level language features. So it's a myth. It's kind of a widespread myth, but there's a myth that the design patterns are universal. They are not universal, you know. Most of the examples in the book are C++. And they actually apply very well to Java because of similar limitations and constraints of the type systems and so on. And then here's very interesting. If we assumed procedural languages, we might have included a design pattern called inheritance, another called encapsulation, and another polymorphism. You see, that's interesting, right? You can say also that design patterns are fixes for missing features in the language. Okay? So Peter Norvig, famous for the AI book, a Stanford professor, he made this presentation in '96 where he said that he was studying the design patterns in light of the languages that he was playing with at the time, Lisp and Dylan, which Dylan is known as a Lisp with syntax. At least that's how I saw it described once. Anyway, and he says that 16 of the 23 patterns in the book have much simpler implementations in Lisp or Dylan than in C++, for at least some uses of the pattern. And there are cases, in fact, where the pattern disappears in a language because it's incorporated. And we'll talk about that. So when he talks about the patterns that become invisible or simpler, those are the features, for instance, first-class types, which is, so first-class functions is more commonly known, right? First-class types is the idea that you can create and modify classes at runtime, right? Which you can do in Python. In Java is much more difficult because you have to generate bytecode on the fly. But then you have, macros, which Python doesn't have, method combination. Anyway, other features that are more obscure. So the iterator pattern is described in the book, right? I'm kind of going to speed up over this. It's pretty well known in the Python community, this pattern. But the interesting thing is it's easy to do something that is iterable, and one way of doing it is to follow the recipe in the design patterns book. But that would be a bad idea because it's very complicated. Thanks to this woman who led the project of the CRU programming language, Barbara Liskov, famous for the Liskov substitution principle, but she also led the team of researchers who did this language that introduced a lot of interesting concepts, like call by sharing, which Python uses, iterators, parallel assignment. Anyway, lots of interesting things came with there. And CRU was the first language that had a for loop like that, which looks very much like a for loop in Python where you unpack tuples, for example, right? Anyway, but the fun thing is that Python incorporated this yield keyword that basically makes the whole pattern disappear. You don't need two classes anymore, the iterable and the iterator, right? Because now when you call iter, you get an iterator automatically. So that's cool, right? So the pattern, as described in the book, doesn't make sense anymore, the implementation of it, right? So one way of thinking about new programming languages is to think about how they are, how the features, what kind of features are in the languages. Like, for instance, Common Lisp is a very influential language, and it's still kind of going and spawning dialects. But it has first-class function and first-class types. It doesn't really have iterators, but because it has macros, you can write, new statements or whatever you need to make iterators work. So you can implement it in a way that seamlessly integrates with the rest. Variable model is references, type checking is dynamic, and the type expression is structure, which means, so type checking dynamic means that the type checking is done at runtime, and type expression means that the criteria for determining whether a type matches is the structure of the object or the methods it has and the attributes. So those two things are functions as objects and classes as objects. So C doesn't have first-class functions, but it has pointers to functions, which in some cases is good enough. It doesn't have first-class types, it doesn't have iterators. The variable model is always value, but the value may be a pointer. The type checking is static and is nominal. So it's based on stuff that you explicitly declare. And then, so Java, you have, those things. Python, this is the situation with Python, and Go, okay? So Go has first-class functions, but doesn't have first-class types. It has iterators, but only for some built-in types. You can't really make your own iterable things. It has a complicated variable model that includes values, pointers as values, references, and references with a little dangling metadata that's important, which is the case of slices. A slice looks like a reference, but actually carries this thing. It's weird. Anyway, and so for instance, to talk about those issues of type checking and type expression, in Python, we've been able to take advantage of new patterns or new ways of coding because of features that have appeared to support. Well, Python always had duck typing. Then at some point in Python 2.6, goose typing appeared. The idea of is instance or is subclass checks at runtime. A lot of use of ABCs to do that. So this is kind of old. Then we had static typing, and more recently, static duck typing, which is the idea when you happen to implement something that looks like a class defined by typing protocol, then your thing satisfies that protocol and it can be used wherever the protocol is required. So, good stuff. And now, those features in other languages. Look at this. So, you see, for instance, Java is only in the bottom right corner, but Go is in 3 corners, see? 3 quadrants. Go has goose typing. It includes syntax to switch on types at runtime. Anyway, so I talked about iterator. That's a pattern that completely disappears. Most patterns may not completely disappear, but will look different. So, for instance, strategy, as described in the book, is a way of selecting on the fly an algorithm to do part of a transaction. Like, for instance, let's say there's an e-commerce company and an order has to compute a total and an amount due that depend on a promotion that may be applied. And then there's different promotions going on that have different rules. But basically they implement a method called discount. So promotion, the strategy is an ABC. It just describes the interface that you have to implement to create a new promotion, right? And the order is a concrete implementation, and the concrete strategies are different implementations of that, right? So that's the way the pattern is described in the book. But, yeah, and then I go into a lot of detail here about the implementations. Say the order, say the promotion ABC, and then the classes that declare themselves as subclasses of promotion, right? In fact, there's no implementation in the promotion. Yeah, because it's an abstract class, of course, yeah. Anyway, so that's it. But you can also do it as a first class function. So instead of instantiating a promotion when you need to instantiate an order, you just pass a reference to a function that computes the discount, right? So that's much simpler because you have first class functions, so you can pass functions around as references, as values, and so on. I'm not going to be reading the code here because it's kind of boring, But there's a longer version of this presentation recorded, but I also added some new content. I like the content about the typing map that I was showing. This is not from the original. Now, to wrap up, I really like this example that I found when I was doing research about my book, for my book. And the thing is, there's this little book about vectorizing. It's called From Python to NumPy, written by a French professor, and it's Creative Commons and so on. And in the first introduction to the subject, he describes a few implementations of code to do a random walk. So it's a random walk on a line, okay? So the let's call it the turtle. The turtle only moves left or right, and it randomly chooses, okay? And so that's the experiment. And so there's a method called walk that you call giving a number of steps. I have a constant there that says 20 steps, just so that it's easier to see what's going on, okay? But you can do it with millions. May take a while. But, yeah. So, when you run it, you see there's a timing there, 34 microseconds, right? And here below is the output. Actually, I regenerate the output. Something weird was happening with Jupyter, because that assignment, walk equals list walker, was not taking. I had a name error in the next cell because of the time it. I don't know what was happening. So I just ran it again so that you can see what kind of output this generates, right? So it's the position. You see the position always varies by 1, right? And it ends up in -3. Anyway, so you see so you have this class, the random walker. It starts with the position, so it has this attribute that is the position. And then the walk method makes it do a number of steps, and it does that by yielding the position, right? And updating the position with this formula that basically generates a -1 or a 1, okay? And then when you you transform that into a list down there, that's where the computations happen. Anyway, so it's interesting because he describes a method that I think it's elegant in Python, being able to use yield, so you don't need to produce, 10 million measurements to do a sample. Then there's the procedural approach, which is just a function, right, that builds a list, okay, called walk. And then there's the vectorized approach, which he calls the vectorized approach. And that's using accumulate, a function from itertools. The itertools library is mostly inspired by Haskell library, right? So basically, you call accumulate and pass it the steps which are the result of random choices, which is a new method. I didn't know it existed. I knew about choice, but random choice is a new function that choices produces a bunch of choices. So anyway, and the thing is, there's okay, and then the last version is this one, and it uses NumPy, right? So this NP random choice function in NumPy makes an array of that size already filled with pickings from those choices of -1 to +1. And then the CumSum generates another array, which is the cumulative sum of the previous values, So that's the output there, right? So you see, that's why it doesn't make sense to say whether Python is or not a functional programming language. We can say that Python allows a functional style of programming for some classes of problems, right? Now, I had this, if you look at the timings, so in the book, the author says that the numpy version is 500 times faster than the object-oriented version, the first one, okay? But here you can see it was, the numpy version was 24 microseconds, rounding up 25 microseconds, and the object-oriented was 14.9, 15 microseconds. So actually, the old version was much faster. But, you know, who knows? Maybe Luis, a friend of mine, was saying, oh, maybe you have to know what you installed when you installed NumPy, because maybe you installed a version that was compiled to calculate using Roman numbers or something. But anyway, and I also, when I talk about this, I always like to say that I like to, you know, there's ways of doing algorithms that are in parallel and distributed and across servers and so on. But I thought it was really funny when this paper came out a couple of years ago called Scalability, but at what cost? So those three authors who are not affiliated with anything because they would be fired, or they wrote a paper analyzing, like a sort of a meta-analysis, analyzing papers about distributed algorithms. And he discovered that the vast majority of the algorithms just were faster in a single core, you know, or in a single machine. So they invented this thing called cost, which is the configuration that outperforms a single thread. Sometimes it could outperform, but you had to have 1,000 cores. Right? Anyway, so to wrap up, the idea is, instead of thinking about programming paradigms, those rigid categories, it's more interesting if you look at features that the languages implement and what those features enable, right? Now, this may look a little bit complicated, but if you then change the layout, okay? So the star feature is present in the A, C, D, and E languages. Interesting. So that may be, you know, streams. So it's, if you're learning a new language, so how do you do streams in this language? Oh, not yet, but it's coming along, you know. Oh, no, everybody does this way, or there's several ways of doing, you know. Anyway, so it's interesting. It's hard to find those fundamentals, but they exist out there. The other version of the talk that is online has like a bibliography, but knowing those fundamentals has allowed me to learn new languages faster, to leverage language features when you know that they are there, so you start using them. Choosing among alternative implementations of, you know, classical patterns or recipes of way of doing things. Make sensible use of design patterns. Debug hard problems. And emulate missing features when they are helpful, right? I remember remember the Palm computers, kind of a last century thing? So the Palm computer was programmed in object-oriented C, not C++ and not Objective-C. It was object-oriented C. It was C with discipline. You know, if the struct was a class, then the first argument was appointed to this instance, you know? So if you follow these rules, you could do everything object-oriented, but you had to be really disciplined. Anyway, you can do it. All right, so thank you very much. I am Ram Garlic at the Fediverse. At the platform formerly known as Twitter, I am Ramalho.org, and that's the repo where the code for this talk is there. and the slides are over there. All right? Thank you so much.
Thanks, Luciano.